We are going to talk about now tree rings. We had a first introduction yesterday. Remember, we were out in the field. You saw us take some course. Now I'm going to give you some information on how we can use tree rings as tools to assess environmental change. And you will use this information that I will present to you sometime next week, because yesterday we did some sampling with Adriana. We collected some cores from areas where we have high nitrogen deposition and low nitrogen deposition, and these samples are going to be analyzed in next week, and you will have some results. So today I'm just going to show you, because I'm not going to be here next week, I'm leaving on Monday. I'm going to show you some graphs of how we can analyze training chronologies, what we obtain from averaging training cores. And I will show you the very strong information that we get in interpreting environmental change. So now I'm very tempted to talk about climatic change, because this is a field that I work on, and we use tree rings in order to assess climatic change, but I'm not going to talk about climatic change. I will try to just show you very basic principles. I do not know if you know about the IPCC reports that project drought in the region. This is from the 2007 report, the recent report 2013 was similar, and it shows the Mediterranean going dry. Now, I've been working in this part of the Mediterranean. We are now somewhere here, I think. Okay, you see this brown color covering parts of the Mediterranean. This means changes in precipitation that are expected towards the end of the century, towards the end of the 21st century. And it's going to be mostly reductions in winter precipitation, because most rainfall comes in the Mediterranean during winter. There will be also some changes in summer precipitation. Now, the basic question that I will ask, and I would like you to think, is what happens if we have a 30% reduction, because this is the responses that we get here. These very brown parts are around 30% reduction. What responses will we have to the ecosystems that we have in the Mediterranean? People coming from Northern Europe would expect the opposite response, higher precipitation. More precipitation goes to Northern Europe and less precipitation to Southern Europe. I'm not going to talk about why, but I'm going to talk about the responses. So we have here in the area, we sampled, and we talked about this during the nice field trip we have with the nice cars. We saw mortality. We saw oaks dying. And we know that we are in an environment where rainfall is a limiting factor. We are discussing about nitrogen, but rainfall is connected to nitrogen. And in natural ecosystems, how is it connected? Because water is the basic principle you need for microbes to function. And microbes are what recycle nutrients. Okay? So water is connected to nutrient recycling. And, well, it's difficult to separate the one from the other, but if we plot temperature and precipitation, and we also have we plot here the climatic range within which particular species, can function, and we shift this towards more dry conditions, warmer and drier. We also have the effect of temperature, which I did not show you before, which is also going to go up. So drought is going to go up, both because of reduction of rainfall and because of increase in temperature. We have vulnerability increasing. We have a higher number of individuals within the population that are going to suffer more. And are the responses that we are seeing in these mountains of dying trees a result of this change? So I'm going to talk about this, and I will show you how we can use tree rings to identify these changes and to give answers to these changes. Now, I showed you before projections, what will happen, what is expected to happen towards the end of the 21st century. The question is, what has happened in the past in the Mediterranean? Has rainfall declined? Are we in a situation where climatic change is already here? Or is it something for the future? Now, this interesting graph, published 2012, shows the variability. This is annual rainfall in the Mediterranean during the last 100 years or so. So, what do you see after 1970? You're in the red zone. And if you take a spatial distribution of this rainfall decline, you will see that some areas are very red. This part, Portugal, we are here, right? Okay, so we are within this range. And parts of northern Africa, but also parts of the Eastern Mediterranean. These are the areas that have been affected most. So, there is no question that rainfall has declined. And there is also no question, I'm not going to talk about temperature, but temperature has also increased in this region. So, drought, we are at a situation in the system which we did not have during the last 100 years. Is it just the last 100 years? Look at this cave. This is time. This is 500 years ago. And there are people that try to reconstruct climate. They use tree rings also to reconstruct climate, but this is another thing. I'm not going to talk about this. What I'm showing you is the outcome of their constructions. And you have rainfall. This is winter rainfall, I think, for the Mediterranean, in relation to an average, 1971-1990 average. So this is an index. And what do you see during the last 500 years? We had some drought in the 18th century, and then so we have ecosystems that have not experienced this rainfall decline in more than at least 500 years. So, do we have a shift in the system? Now, for ecologists that work with ecosystems, this should be a very important question. Because normally, if we have such strong responses, and we are at a system, some strong driving forces, and we are at the system where responses are related to this factor, we should see big changes already. It should be evident everywhere. Okay? And I will try to show you some examples where we see this. We talked about mortality. Okay? Species dying, going beyond the threshold that they can survive. And there's a nice paper, a very nice paper, by Allen et al. It's from the United States. They took a global, they started noticing, because they had the mortality problem in the United States as well. And they are foresters from the United States. And they said, okay, is it only the United States? And they tried to make global synthesis of papers that have been published with mortality events during the last 30 years within this, or that period here. And this is their paper on their graph on Europe. They have for each continent. And you see areas where mortality hasn't been observed in different species and has been documented to be related to drought. So all the points here refer to papers that have been published that show the mortality that scientists have been relating to drought. In cedar forests here, Pinus sylvestris here up in the mountains. I don't see anything for Portugal. You should try to work here, the Alps. And I've been working on number 13. This was when I started my PhD. And that's an island called Samos. And this is the system that I was working on. It's a Pinus bruta system. It's similar to Pinus halepensis. I don't know if you know about Pinus halepensis. I'd say it's similar to Pinus pinaster, maybe. Something like it. Ecologically, maybe it's similar. And we also have some junipers. This is low elevation. All of these are high elevation. This was the first paper showing that at low elevation, this is at 200 meters above sea level, we have pines that are supposed to be drought resistant. They're supposed to be the most resistant to drought, started to die because of changes in rainfall. Well, we didn't know that it was change in rainfall. I will show you how to use trimmings to identify this. But at this scale, we saw that they were desiccating, they were becoming brown, and that these, we found out later, were 80-year-old trees. So they had never experienced this type of effect before. And it was not only this species. In the same area, this is a southern site. Remember what we learned today when we were at the castle, and Adriana talked to you about the southern exposition. So this area gets much more solar radiation. It's heated up more during summertime. We had the Mica shrub and the Frigana shrub vegetation also dying. This is the year 2000. So we have junipers, Filirea, Quercus crucifera, oaks, and so on, and all they all died. It was during the same year that the pines also died. It's interesting to discuss about recovery in this situation because this species, and this because they sprout, managed to keep their position within the system the next years. But these, especially the junipers, they did not. They're now still dead. They have not been recolonized in this place. So we have species of different, how can I say, ability to withstand drought, being affected, and then we see that some recover, some do not recover. So how can we use tree rings? Tree rings is the science of dendrochronology. Dendro means tree, chronology, it comes from the Greek word chronos, which means time. So knowing the time that something happened, and knowing the time that trees responded to something. Let's say this is a very, let's say, vague interpretation. And let's go to some of the basics, because I don't know if you taught this, but it's something that I also talked to you about yesterday. We have the zone of cambium cells here. We know that these are the cells that are divided, and they have the ability, when divided, to produce a phloem, where sugars are transmitted from, and to produce xylem. And we talked about these wide vessels and the short vessels that construct one ring. Okay? Wide vessels during the beginning of the growing season to transport lots of water, and then during the end of the season, short vessels with thicker cellular walls, lots of lignin that are used to support the weight of the tree. And this band and this band, you can see it's very easy to identify, and counting them, you get the age of the tree. Okay? Now, I'm not only going to talk about the age of the tree, I'm also going to talk about what information we get by measuring this width. Okay? Because this width, as we also talked yesterday, is a measure of, is an indicator of how productive the tree was. Okay? High width, a big width. Wide rings means productive. Small rings means not so productive. Okay, and this is another thing to consider. Are all trees sensitive to everything? What information do we record in tree rings? In order to be able to record drought, we need to find trees that are at their xeric margin of distribution. In a particular species, each tree species has a genetic potential, and it can survive within a particular range. In terms of climate, it has what we say thermal margin, where cold, let's say, can limit the particular existence of the particular species, and it has xeric margin, where drought has a limit. So if you go up on a mountain, you will see the different zones of vegetation. Okay? You've already, all of you noticed that. If you climb up a mountain, you see different species up at the top and different at the bottom. And each of these species has a particular range within which it can survive. For example, pines, low elevation pines, Pinus glutea, Pinus pinaster, or you can put here Quercus suber, doesn't matter, has a thermal limit that is xeric limit that is determined by precipitation, and low temperatures also limited up to a particular altitude. Because cold also affects cambium, so it does not allow cells to divide. While here there's not enough water for cells to divide. So it's two ends. And if you go up higher, this is from Pinus niger, this is another pine, you have another species that is more adapted to cold conditions. It can go up at higher elevations, but it is also affected by drought at some point here. So, in order to study drought, we need to find the right species, and we need to sample at where the species would be most sensitive to the particular climatic trend. Now, this is a cross-section. We talked about this yesterday. I showed you some cross-sections where we had the logs there. And you see the wide rings and the less wide rings. So this means productive. Okay. Maybe it depends. Okay. So this is productive, and this is less productive. Okay, you can see the differences. This compared to this, for example, or this compared to this. Okay. So this means in a particular tree, this was from also low elevation. This means that the particular tree is sensitive to variability, and we need to identify what exactly does this variability mean. You also saw this, how we record with increment water. Adriana can tell you stories from yesterday at dinner, how easy this is. Easy to find. Oaks are, they like their trees. They don't want us to get this information, but we managed to work with them. And this is how we count number of rings. Okay, we date them and we measure the width. And this produces a time series. What do we mean by time series? We have one axis, which is the width, and another axis, which is time. Years. 1970, 71, 72, 70, whatever. Okay? So this is how we work. Let's go to some papers that show the responses to the drought intensification that we saw in the Eastern Mediterranean. This is from climatic change. And this is messy, I know, but I will help you. If anybody of you visited Greece, raise your hand. I know. Okay, so which island did you visit? Okay, so this is Creta. Athens is here. Okay, this is the Peloponnese. I will give you hints of which islands to visit later. Okay, but what we have here is the decline in precipitation that this part of the world received during this period, 1955-2001. So this is percent per decade. So 10 means that during this period, rainfall declined by 10% per decade. Okay? This is a lot. 10% per decade. Because we are the zone that we discussed before. Rainfall going down. So lots of decline here. Here, not so much. So what we did was we designed a strategy to sample forests where rainfall would have shown a significant decline, and it's the gray areas. All the gray areas show a significant decline from different rainfall regimes. So Western Greece gets about around 907 millimeters of rainfall. Here you get 150 millimeters. Here it was 405. Here again rainfall increases, 754, and here it also decreases. So from different areas, but still within the range of significant rainfall decline. And in all these ranges, this is a vegetation map. The black describes the thermal Mediterranean vegetation belt, which is the most warm and driest belt. So we took forests from these 4 islands. It's the island of Zakynthos, Skiros, Samos, and from the eastern part of Crete. And this is actually the rainfall regime of this area, of these areas. You can see the decline that you see here in percentage. This is on a time series, and this is a mean of the 4 sites that we sampled. Okay? So there is a decline during this period. We have years of drought, and I know that you will be very curious to see how the trees responded during particular years. Do they follow this? Okay, I need to show you the forests. This is the forest actually that we worked with. Low elevation, 200 millimeters, 150, meters, 200 meters, 150 meters in Samos. A bit higher in Skiros and a bit higher in Yaranta, but still within the same range of the thermal Mediterranean vegetation belt. The number of trees, slope, we used slope, we went to southern slopes, we wanted to have the highest impact from drought. And this is the first results from tree width, measuring tree width. So here we have the width of the rings for 3 different age classes, old trees, medium trees, and young trees. Now, the first thing you want to identify when you see tree rings and time series like this, which we call chronologies, is if they are synchronous. Synchronicity is the first thing in order to identify that you have trees that are sensitive to climate. And why synchronicity? Because this means that during a particular year you have a driver, you have a drought, you have many trees that should show a drought response. They should show narrow rings. Okay? If only one tree shows up, it means that there's no effect. But if all trees show the same effect, it means that there is a strong driver for productivity with a particular site. So, what do you see in this situation regarding synchronicity? Are they synchronous? They are. Okay? They are. They show high synchronicity when in each site, the 3 different age classes show this. And if we average all the 3 age groups, and we have this from all the 4 regions, we have this mean growth. And the second thing that we wanted to address is, okay, we have synchronicity when we have, well, I'll show you later, when we have dry years, we find that growth is reduced, but how much? So here we took these periods when the trees were of similar age. We talked about this yesterday, but this is important because we have the other problem of age trend, so we need to have trees of similar age to compare. And we made the graphs. And what do they show? For around 20 years of growth, they show decline, 46%, 24%, beginning of the century, mid-century, compared to the last 20 years. More or less the same situation in every site. So, rainfall, declining. These are the same bars for the same periods we had before for growth. And here you have the first connection between the two. On your left, you have tree growth, and on your right, you have precipitation. If rainfall declines, we would expect growth to decline. So do you see this response? Rainfall declines, growth declines. Okay? So, were these trees affected by the drought we were talking about? They were. Beyond question. Yes?
This is correlation, but it doesn't mean it is the drought the cause, right?
Okay, nice question. Keep this, we'll talk about this later. Yes, this is a correlation between the two. This is just to show that A goes down, B also goes down. And let's see other factors. This is the same analysis as before, but here we grouped growth in 10-year, let's say, averages. Okay, to have general outlook of the area that we studied. We had all trees that went back to 1780. And this is the 10 years of growth, and these are all now 4 sites. And this is the decline in rainfall. So this is 10 years, and this is 10-year running means of rainfall. Okay, this is what the climatologists told us that happens. And what do you see regarding the decline in growth? The decline in growth, just as rainfall declines, growth declines. So, 2 things that, one, in theory that causes is the basic driver for growth, and you see the response here. It's like something that is like a smoking gun, okay? And you know about CO2? CO2 is going up in the atmosphere. This is what climatologists tell us, or atmospheric scientists tell us, it causes global warming and so on. And they tell us that if you have, well, they don't tell us. Some people believe that because we have more CO2, trees will be fertilized by this CO2. Okay? You've heard about this somewhere? So this is carbon dioxide during the last 100 years, and it's going up. So is growth following carbon dioxide, or is it following rainfall decline? Clearly rainfall decline. It does not care about CO2. CO2 is causing rainfall to decline. This is what the trees care about. But there's no fertilization. Okay? I don't know if you would add nitrogen. That would be interesting. But you would also need to add water. This is my understanding. Without water, you will not see anything. Okay, so we have the decline that is matched with the only driver we can think of that could have affected. These areas are not close together. This is around 500 kilometers or more, 600 kilometers probably. I think it's more. This is 600, this is around 1,000 kilometers. So, 4 regions that show the same thing, where we would expect them to have the same response. Now, this analysis was until 2001. And there's the question, has this phenomenon of growth decline continued and mortality during the next years? Now, I know you do not like pines, you like oaks. So, I'm going to talk about oaks. Okay? And I'm going to talk about oaks that almost died from this part of Greece. This is, I studied around here, so this was the University of Patras where I had my diploma. And it's this area here, which is also high rainfall. It's around 800 millimeters there. It's similar to the habitats that we sampled with cork oak, but there they are occupied by...
We'll have here 10 minutes. So
okay, I'll try to wrap it up.
to give a little time.
Yeah. I'm getting somewhere, so... Okay. So this is a similar species. It's called Quercus itaburensis, subspecies macrolepis. We'll call it Quercus macrolepis for short. It occupies the same more or less habitat. Wet zones close to sea level. You see the sea level here. And what happened in August 2007? You see they're becoming brown, losing foliage. These trees are deciduous during winter time. And during summertime, they have foliage. They are deep-rooted, they can take water from the water table below ground. And you see the difference. This is not healthy, this is healthy. Something happened during that time. So this was a time where we had a big heat wave, and this is a response after the big heat wave in Greece, in this area. It was the same year that we had also very big fire events in Greece, the largest in our history. So it was not again only one species that was affected, it was all species within the habitat, but the ones that were more sensitive to drought. Pistacia lendiscus, for example, was not affected, which is the most drought-tolerant species in that ecosystem. But all the others, they were affected. You can see them growing. These are oaks. These are young oaks now, that they also show that they became brown. So you see the little oaks. This oak is just 2 to 3 years old, and it also was also desiccated. Usually the young ones were affected most from this drought. It's likely because they had a more shallow root system. So during my postdoc, we had an idea of continuing the investigation, not on pines but on oaks. We took oaks from this area and this area. And we also took another species just for confirmation. This is the juniper, Dimitrios phoenicia. And we tried also to sample tree rings and get the responses. And this is a response from oaks from the area where you saw almost mortality. I will tell you about this later. They did not die 100%, but they were affected. So this is tree growth. These are more than 100-year-old trees. And this is the decline in rainfall for the last 20 years. Decline in growth, decline in rainfall. So it's not just 1 year that affected them, they had a gradual decline. This is 20-year means. And this is from the eastern part of the Peloponnese, where you see the decline in rainfall and growth, which is much steeper. I'm very curious to see if we sample these oaks from this region, if we get a similar response. You see this decline in growth, that could be matching the decline in rainfall. And we talking about the other species, Dimitrios phoenicia, and it also shows the same thing. Decline in growth following the decline in rainfall. This is for 20 years running means. Again here. All of this discussion was for secondary growth. If we go into primary growth and we talk about needle length, you see needle length being affected. This is needles of the year 2000, the year that we saw before, that we had the drought in Samos. And you see that compared to the previous years, needles were short. So productivity is definitely affected by drought. And I'm just going to go very briefly on, because we don't have time anymore, on these years of drought, which caused a phenomenon. It was not just 1 year that caused the responses that we showed before. We identified by correlation analysis that if we take tree rings and we take precipitation and try to make correlations with different categories of precipitation, monthly, seasonal, annual, and multiple year, what happened in the past. We found out that the best correlations here are for 2 years or for 3 or 4 years. So it's the previous years accumulated rainfall that had affected growth, not just one year, one season. And we did a more complex correlation analysis. I'm not going to go in details, but we can do analysis like this, and we found out that during periods, this is precipitation, high rainfall, this is growth, and this is response to a particular driver. This shows 2-year rainfall. When we had wet conditions, these pines responded to 2-year rainfall, and when we had very dry conditions, they responded to the previous 5 years of rainfall. Imagine, one ring produced by the rainfall of the previous 5 years. There is a long memory in this system. It's not just what we see, we feel. It's also the past. And this can mostly be explained if we consider ground, below ground, and water being stratified at these layers. So we have rainfall of this year. Next year it will be lower. 2 years from now it will be even lower. So there's a stratification of rainfall below ground, and deep roots can access this water. So it's actually the drought of these 2 years, 1997 and 2000, that caused this response. And this appeared in the cover page of Global Tree Biology, because we showed that this is a severe impact on the ecosystem. These incidents were repeated, and they are repeating now. I was a couple of years ago in Israel, and we studied the response to this desiccation from the 2011 drought. Okay, so the incidents are repeating themselves. In Cyprus, we also have 2013 mortality, and there are different ways where we can work with this. It's not just with trees, but trees are a very powerful tool. You need to have them in order to have a basic assessment of what's going on. So what you will do, Adriana will show you, is these growth differences between the two sites. The one with the nitrogen deposition and the one without the nitrogen deposition. And you will compare growth, and it's likely that you will also have a time series of growth, and you will see in which cases the growth between the two the difference is bigger and when it's lower. And it's likely if we put rainfall at the same graph, we will see what happens when we have more rainfall and what happens when we get less rainfall. And I'm very curious to see the response. Okay, so thank you for your attention. Any questions? I'm here, but you can also email me things and I can show you papers and things like that. Okay, thank you. So now I have to compete with dinner, so it's impossible.
Have you tried other measures besides the average of the trees?
Usually the average is the most powerful tool because, as I tried to explain yesterday, you have other factors that can affect an individual tree. Mm-hmm. So you need an average of at least 20 or 30 trees to have the same signal. These here responses that I'm showing came from a number of trees. There are around 82 trees here that have been showing the same response. Let's go to this.
That one is interesting. Sorry.
This one? No, I cannot see anymore. This one?
No.
This one?
Yes.
Okay, yeah. This is interesting, yes.
Because it's happening for me, it's an increase in variability.
It's an increase in variability. Yes, there is an increase in variability. This is true. This is true. You see, some go up and some go down. This is true.
Means that they are very heterogeneous.
But yeah. There is heterogeneity. I agree. The problem in some.
If you go to previous slide, can you just go to previous slide?
Yes.
For example, I like very much the maximum here. The maximum, because the maximums are always going down.
And I will tell you why this heterogeneity exists. No. Sorry. What do we do? Lights, please. I don't know. Okay. We're going somewhere now. No. This heterogeneity has to do with sampling only one side of oak. because these are oaks, and it's very difficult to sample them. So in this case, the sampling that we selected was just one site, and it's likely that we got also effects of bending and things like that. And that has not been published, what I showed you. So because we have big problems. If we take two sites, we narrow this variability. So it's likely because of sampling and not because of climate and things like that. Other things you can do in order to I'm not good with these things. Okay? No, I managed to do it. So, the other things that you can do, but I did not talk about them because we don't have time, is stable isotope analysis. And you can get the responses of the trees to drought based on isotopes. This is, there's no time to show this, but this shows, for example, again here, we have rainfall from the same region of Samos, and this is delta 13C. This shows drier, and this shows wetter conditions. More stress, less stress. Okay? So isotopes confirm, this is treating it. You see how they go together? Okay? So it shows that physiologically there was a strong effect as well. Okay, we found this later. And if we go to another interesting, I'm just going to finish with that, because we talked about deeper soil horizons. If we use oxygen isotopes, you have more negative oxygen and water here. You have O18 is an isotope where you have a surface that is evaporating. You get more O18 inside because it's a heavy isotope. It does not go into the atmosphere easily. So in this area here, you have more O18 in water, and here you have less. And what we found when we analyzed 18O is that, let's find 18O. Okay, here. It goes down. Okay, which means that these trees are actually using water from below ground as drought intensifies. Okay, and this is also information you get from cheerings. You need to make them into powder and put them in a mass spectrometer machine to measure these isotopes. But this is also powerful information. There are lots of things you can do with cheerings. Okay? Any other questions? Yes.
I think sometimes it's a little bit tricky when you have this, I don't know if it happened with you in this work, when you have extreme conditions and then the weight is reduced because the production of biomass is reduced, but then the 13C and the signal that you get is before they start. So you have this kind of information from the good part of the year, and then you have this mixed information. So you have a good connection, but sometimes you don't, right? I don't know if it happened with you, but
this is true. This is true.
This is
true. This is true. So what we did, we took this into consideration, and in our analysis, we also did a segment by segment analysis of rings, in particular years, wet and dry years. And we had the dendrometers, and we could monitor growth during the same. Okay, let's go see the dendrometers here. So it's what, like you said, this is a wet year, and this is a dry year, and this is a growth cessation during the dry year, and this is during the wet year. The dry year, you see, more months where nothing happens. The wet year, and of course, productivity is much higher here than here. But let's say we were lucky. We were a bit lucky. So trees record information when they grow. Okay? When they do not grow, they will not, for example, your point, capture summer drought conditions. But they do actually. Why? And this is another thing, physiology of trees that we are still experimenting with. Okay? Because there's a carryover effect. Photosynthesis does not really stop during summertime. It continues on. It goes on. There's not enough water to produce growth, but photosynthesis is occurring and it accumulates. And when you have the first autumn rains, these signals are incorporated into the wood. So if you analyze entire rings, you get the information from somewhere, but you get it in autumn. If you analyze rings only in early wood, you will not get this information. So this is another point of this paper, 2013, where we did this analysis and we found out that you get the signal in autumn. So if you take entire rings, you get a good correlation, and these were the correlations which I showed you before. So yes, you need to know how your system works in order to interpret correctly. You need to know how what the limitations are, but you can get lucky as well. Okay, we did not expect to see this, but we found out that it works. Okay, now we got to technical.